Share screen. Share. Okay. Is the screen visible? Can you see the presentation?
Yes.
Okay. All right. So first of all, thanks for giving me this opportunity, and also thanks to Marius for this nice introduction, which actually gives me the opportunity to just continue basically from what he was saying in his last slides. So the work I'm going to talk about is a bit of a review, but also based on these two papers, especially the first one here with Fabrizio Rontinelli and Guillermo Ballesteros. And I will essentially I want to review possibilities to address the Hubble tension from the model building point of view. And in particular, I will review solutions which we may call early time solution, in the sense that we will exactly try to reduce the sound horizon, exactly as Marius was just saying. Okay, so I will first of all show what is a natural, in my opinion, a natural way of doing it, which is to add radiation to lambda CDM, to add the dark radiation. And however, this model is not a full solution, is simply alleviating the tension. Then I will enter into this business of the so-called early dark energy models. There was a question about it 1 minute ago. And then I will also show that our recent work perhaps opens the possibility of addressing the H0 tension by varying the Newton constant in time. Okay, this is actually a solution which is not a full solution, is just alleviating the tension, and it's quite kind of similar to the dark radiation solution. Okay, so thanks to the introduction from Marius, I can skip the first slides and just go to this one. So what I want to do is to modify physics around recombination, or perhaps a bit before, around matter radiation equality. And the goal is to reduce the sound horizon. So we have seen the expression of the sound horizon from previous talk. And essentially it's an integral of this function, which contains two quantities, the sound speed of the fluid and the Hubble rate, the expansion rate. Okay. Now it is very, I would say it is difficult to change the sound speed, because this is determined by the baryon, by omega baryon. And as we saw in the previous talk, if you change omega baryon, you will change relative height of the peaks. So it's a very well measured quantity. It's difficult to play with it. Therefore, most solutions, they actually try to change the other quantity, which is h of z. And so this is what we will try to do, to change the Hubble rate around the recombination. Okay, now this is not so easy, because we want to do that, but we want to keep all the important angular scales of the CMB fixed, because the lambda CDM fit of the CMB is quite good, and we don't want to destroy it. So what are the important angular scales? Well, first of all, there is the sound horizon, well, theta s, which just saw it. So we want to keep fixed theta s, and this is precisely what solves the Hubble tension if we decrease RS. But then there is also theta equality, let's call it like that, which is the ratio between the matter radiation equality horizon, if you want, and the distance from us to the matter radiation equality era. This was also discussed in the previous talk. And then there is a third angular scale, which is the damping scale, which was also discussed in the previous talk, also called the photon diffusion damping or silk damping. And this last angular scale actually tells us where the spectrum starts becoming exponentially suppressed. So there is this exponential tail here, and if we change theta d, we will suppress more or less the spectrum. Okay, so we cannot play much with these three thetas. Okay, so what about dark radiation? Well, we can we can simply add around 7% of radiation, which is in some dark sector, and this will just as simple as that induce an increase of about 7% in energy density, and so in the Hubble parameter. Sorry, and so it will decrease RS by 7%. Okay. So this is a simple, well-motivated possibility, and there are many candidates. There are sterile neutrinos, there could be axions, there could be some dark sectors, even gravitational waves, and many possibilities in this model. Typically, it is parameterized by this quantity called the delta N effective, which is nothing else than the number of effective neutrinos, which is proportional to the fraction of radiation density over the photon density, which is here, minus the standard model value, which is about 3. Okay? So this is a very appealing approach. Now, can we keep equality fixed? We want to keep theta equality fixed. Well, this is also very simple in this context, because if we increase omega radiation, we just need to increase accordingly omega matter to keep fixed the equality epoch. Okay, so this is simple to do. Theta S, we just saw it, that if we decrease RS, then automatically the distance has also to decrease, and therefore H naught increases. Okay, that's how we address the Hubble tension. But then the problem actually arises with the damping scale. So the damping scale is essentially the mean given by the mean free path of a photon which scatters. It's a random walk, so there are many scattering events. And essentially, by nature, this quantity is a variance because this is a random walk. Therefore, this quantity is a quadratic quantity. And in fact, indeed, the equation is that the damping radius, if you want, the damping distance square is given by this integral, which is similar, if you want, to the sound horizon integral. But the important difference is that this goes like a square of a distance. Therefore, if we modify H by delta H, then this RD gets modified by a factor of -1/2 delta H over H. Okay, so this factor of 2 is crucial because it is different from what happens to RS. RS was changed by a factor of 1. This tells us that for dark radiation, we don't get the same relative correction to RS and RD, and therefore these two angles, theta D and theta S, they change differently. They are not, the ratio is not fixed, and this is not something that works when you fit the CMB. Okay, so this is the problem with dark radiation. Nonetheless, the tension is actually alleviated because the mechanism works to some extent, and one can get H naught of about 70 when combining all data, meaning also when combining supernova data. Is this a hint for dark radiation? Well, a recent fit that we performed in this paper tells us that delta N effective is 0.33, and the error bar is actually less than half of it. So it seems to be a hint for dark radiation. The chi-square goes down by about -5.5. However, one may be worried by the fact that we are combining data sets which are actually in tension, which means the local value and all the rest. Okay. So let me also spend a word about correlation of parameters, which is the reason why the dark radiation solution to some extent works. Even if this relation is bad, there is a suppression in the damping tail. There is enough freedom in the CMB to compensate partially this extra suppression in damping tail by changing the primordial spectrum, by changing the spectral index and the amplitude by some amount. And this also can be compensated by higher omega matter. So there is a correlation between parameters which allows us to have a partial solution. As an example, a delta N effective of 0.3, for instance, this was worked out in this paper, could be obtained from thermal axions. And this happens, for instance, if the axion is coupled to leptons with a coupling strength, with a coupling a decay constant, let's call it, of order of 5×10⁶ GeV. Okay. If there are questions, I will comment more on this. However, now let me show the plot that Marius was showing before. The question is, can we do better than an effective? Now, this plot has two colors, and the orange color is the damping scale, and the blue is the sound horizon. And essentially, to compute the sound horizon or the damping scale, one has to perform an integral, and it is weighted by these two functions that you see here. So you can see that these two functions, they have a support in slightly different regions. Therefore, by having a contribution to the energy density that scales in a non-trivial way, one could try to give more weight to, for instance, to the blue compared to the orange. And therefore, one could try to get that delta RD over RD is equal to delta RS to RS instead of this factor of 1/2. Okay? So by having an extra component of energy density that scales different from radiation, one can try to play this game and solve better the H potential. In particular, here we have one candidate which has a peak just before recombination, and then it decays slowly. Well, actually, it decays like matter or radiation, depending on the model. So this is what is basically the idea of these early dark energy models. Is nothing else than having a scalar field which is frozen, and then a sudden injection of energy before recombination. So as you know, the scalar field obeys the Klein-Gordon equation, and if the mass of the field, which is nothing else than the square root of the second derivative of the potential, is much smaller than h, the field is frozen, and after that the field starts rolling, and when it rolls, it can redshift faster than matter or radiation, depending on the shape of the potential. So one of these attempts is called, well, it is simply a polynomial potential with, and the best fit power is actually 4. So it's a 5 to the 4 theory. This theory has an injection of energy which is quite large around the equality, and then it decays like radiation actually. Of course, this injection of energy is completely fine-tuned because one has to choose the mass such that this happens exactly at the equality. Okay. The chi-square is a little bit better than an effective. And well, one can also build some criterion to decide if this model is better or worse. For instance, this Akaike information criterion, which penalizes a model by 2 times the number of extra parameters. And if you look at this, then actually the model is not better than an effective. However, it's an interesting idea, let's say, to keep in mind. Then a similar proposal is actually a potential which looks like a bit like an axion. So there is a cosine potential. However, it's not quite an axion because of this power n. And actually the best fit power is 3. So this is an axion potential to the power 3, which, as far as I know, fundamentally it has actually little justification. Also here, there are more parameters. There are actually 4 free parameters. Therefore, we are increasing a lot the number of parameters, but the chi-square that we get is much better, is -14. And so even this criterion points towards, for this model, as a better solution than the previous ones. Why is this fitting better? Well, this is actually not completely clear, at least not to me, but it has to do also with the perturbations. So when we have an extra fluid, in this case a scalar, we have to include perturbations of density and velocity. I'm not going to enter into the details. However, whenever one adds perturbations, this affects the CMB. And in particular, there is a quantity which is delta P over delta rho, and this is called the sound speed. And this quantity has been shown to be very important actually to solve the H0 tension. Just to give an example, radiation has all these quantities W, CS square, CA square equal to 1/3, matter has them equal to 0. For a scalar field, it's a bit more complicated. So let's, for instance, when we look at an effective solution, the perturbations are important because they induce an additional effect, which is a phase shift in the CMB. So if you change from an effective 3 to an effective 2, you can see that there is a phase shift in the CMB. So for a scalar field, one has to perturb the scalar field equation, but then, well, in many cases, what has been done in the literature is to consider the background, which is often oscillating, to average over these oscillations, and then to build an effective sound speed, which is nothing else than the time average of delta p over delta rho. And this effective sound speed is actually 1 for very large k, and it's some different number for small k's. Now, why this is important? Well, it has been shown that actually without including perturbations, these early dark energy models, they fail to improve on H0 tension. So this is essential. And then there is also this paper by Lin, Benevento, Hu, and Raveri that shows that for a given equation of state of this early dark energy fluid, for instance, let's say 0.5, then we actually have to choose the appropriate sound speed to get a good fit of the data. For instance, we need a speed of sound which is less than 1 to have a good fit for 0.5. And this is actually one of the reasons why the models with a cosine potential fits better, because there is more freedom and one can choose CS basically suitable to fit the data, because we are on top of the hill, and in that position CS is actually better. Okay, now problems with this approach. The worst problem, in my opinion, is this coincidence problem. Why this transition between frozen and dynamical happens around the quality? This is in these models is put ad hoc, is a fine-tuned choice. So moreover, this the last model that I presented has 4 extra parameters, and the potential is not clear if this is well motivated. So in my opinion, it is necessary to think about physically motivated approaches to the H0 tension. So something that we have tried is to replace dark radiation, the solution with dark radiation, with a solution where instead of changing the Hubble rate because of an extra component of rho, we change the Hubble rate because we change the Planck mass around the recombination. Okay, so this is not something new conceptually. If you want, this is beyond the standard Einstein gravity possibility, and we have a lambda CDM plus a variation in G Newton. Okay? So we will have to do with this quantity, which is delta G Newton over G Newton today, and we try to build the simplest model that performs, that realizes this. And you immediately realize that you need at least 2 extra parameters, because one is the value of G Newton at recombination, and the other one is the rate of variation during the cosmological evolution. It's setting the rate of variation. Then there are important observational constraints. The first constraint is that BBN fixes, gives you an upper bound on how much you can vary G Newton. And the conservative constraint is about 15–20%. There are more recent and stronger constraints. However, these are very recent, and well, we have not included them in the analysis. And then even more difficult to satisfy is the solar system test of gravity. So as it is well known, there are the so-called post-Newtonian parameters, which parameterize deviations from GR in the solar system, and these are very well measured quantities. In particular, this quantity gamma Pn minus 1 is of the order of 10 to minus 5, so we cannot deviate more than this in the solar system. Okay, so the simplest possibility that we try to use is a scalar tensor theory of gravity, of the Brans-Dicke type, if you want, where there is a function of a scalar field coupled to the Ricci scalar. This is also called a non-minimal coupling, and for instance, it became popular in Higgs inflation models. So the simplest choice is to have a function with a minimum at 0, and this minimum has a non-zero value, which is this 1 here. So we took, basically the function is 1 plus beta phi square. Okay, simplest thing that you can try. All right, so the variation of the Planck mass square is actually beta phi square, nothing else than that. So the idea in this type of model is that the equation of motion itself contains the Ricci scalar here. And now there is a nice feature that during radiation domination, the Ricci scalar is negligible compared to h squared. Therefore, the field is stuck and is frozen. And then during matter domination, the field starts rolling if this term is of the same order of h. And this happens when the coupling constant is order 1, okay, or 0.5 or something like that. Therefore, this is a very natural way of having a field which is frozen and then starts rolling at matter radiation equality, which makes this approach, in my opinion, motivated. And here you can see that the field is frozen and then it starts performing oscillations, or for other choices of parameters is frozen and then it rolls down to a smaller value. Okay. The scaling of energy density is a little bit like delta N effective at early time, but then it actually redshifts faster, like a to the minus 4.5. So summarizing, well, then we have to confront with data, and so we perform a fit to the CMB, adding also BAO and supernovae, and we also added the post-Newtonian constraint, the so-called Cassini bound. So we simply included a Gaussian constraint on gamma minus 1, assuming that this is given by the value of the field at late time, at the present time. So by combining all this, these are the results that we get. A variation of G Newton of about 5–10%, okay? It can give a value of H0, which is slightly larger than lambda CDM, and it's around 69.5, the central value. And the initial value of the field that we need during radiation domination is of the order of 0.3, 0.4 Planck masses. What about H0? Actually, this model, in the end of the day, although it looked like a motivated model, in the end of the day, it performs a bit worse than delta N effective, okay? Because H0 is not as large as delta N effective. Finally, one word about omega dark matter. In this model, we don't need an extra component of dark matter to compensate for extra radiation, as for the delta N effective model. Therefore, omega CDM is not very different from the lambda CDM values. Okay. Here you can see that a 7% variation of delta G Newton is basically equivalent to a 0.3 delta N effective value. The chi-square is, however, a bit worse in the delta G Newton model than in delta N effective. Therefore, this is, we can call it as an attempt more than a solution. Okay. However, a preliminary statement is also that if we remove the post-Newtonian constraint, then the delta G Newton seems to perform slightly better actually than delta N effective. And this is promising because it is possible to think of this model as a framework, as an inspiration to alleviate the Hubble tension. However, which has some pros, and the pros is that there is a built-in dynamical transition at equality, and there are only 2 extra parameters so far, and maybe there is a small shift of omega matter, for instance. However, there are limitations, as I said. The limitations is that there are post-Newtonian constraints and BBN constraints, and also that the scalar has been assumed to be massless. So if you also add the mass, the model becomes a bit more complicated. However, there are I think, some ideas that one can think about, and for instance, to apply screening mechanism at late time to avoid these post-Newtonian constraints, something like the Weinstein mechanism. This will require, however, probably more sophisticated scalar tensor theories. Or an alternative idea is to use this type of transition generated by the Ricci scalar as a trigger mechanism for some kind of dynamical transition at equality. Okay, so these are ideas that could be used. And with this, I conclude. Then I'm ready to take questions.
Thank you very much. So we're actually a couple of questions in chat already. So from Albert, how does the proposed solution with Browns-Dicke compare with existing constraints on Browns-Dicke theory?
Well, this is precisely the post-Newtonian constraints. So this type of model is not pure Browns, is not what is traditionally called the Browns-Dicke model, because the Browns-Dicke model does not contain the constant. Let me show you the Lagrangian here. Yes. So in the function f, the traditional Browns-Dicke model does not contain this one. Okay. So the constraints are completely different. Now, if you include this constant one, essentially you are creating a minimum here with non-zero value, and the post-Newtonian parameters are become zero if the field rolls to the minimum. Okay, so just by having phi reaching a very small final value, you can satisfy the post-Newtonian parameters. Okay. But in the pure Browns-Dicke, you cannot do that. In the traditional Browns-Dicke.
Okay, there's another question that how could one distinguish dark radiation from ordinary radiation, and what are the precise differences?
I'm not sure I understand in which sense distinguish, using what? Using direct observations, using CMB? The question is not totally clear to me. So I see a new question. Why do you call it dark? Well, I call it dark because it does not couple to the standard model. Or it couples very, very little, like in the case of axions or sterile neutrinos. So not sure if I answered the question.
Okay, and can you see, or there's another question from Roberto Francischini. Can you comment on why the PPN limits are stronger than BBN? Because the solar system sees GN now, so it cannot maybe very well constrain GN at earlier times.
The system 1 seems to be about G Newton now, hence poorly constraining G Newton at earlier times. Can you say more on how PPN said? Well, actually, okay, let me say again. The PPN limit has to do with the final value of phi, not with the initial, not with what happens at a recombination, of course. And so it actually depends on the specific function f of phi that you are choosing. So you could choose, for instance, a more steep or less steep than quadratic function, and then the PPN limits would be maybe stronger or weaker. We have not tried fully, so I cannot really answer if they are more stringent or less stringent. However, you can immediately see that if you increase beta, the transition, the field has a transition from the initial to the final value, which is much more sharp and rapid, and therefore you have a final value of phi, which is smaller. However, gamma post-Newtonian -1, it contains also beta. So it contains, what is it? Let me see. Yeah, it also contains beta square, phi naught square. So if you increase beta, you gain because phi naught is smaller, but you lose because beta is larger. Therefore, well, there is an interplay with these two parameters, and it actually depends on the specific shape of function f that you are using. Let me also comment about BBN. Well, so for BBN, maybe this figure here is instructive in the sense that you can see that by applying BBN constraints, maybe we will have to discard two large variations of G Newton, right? So let's say that more than 10% is excluded, then we would cut this figure into two, basically, and the lower part of the figure would be excluded. However, you can see that there is still this corner here, which allows H naught of about 70, and it has a moderately a moderate deviation from 0 of delta G Newton over G Newton, this corresponds probably to 4%. Therefore, I'm not really worried by BBN, by adding constraints from BBN because of this plot here. And I think PPN is more of a challenge.
All right, I think it's time to move on. So thanks again for this very nice talk. And our next speaker is Yasin Ali Hamoud.